Okay. Hi, everyone. I am Doug Dow, and I'm a fifth-year PhD candidate at NYU. My research is in probability, and I'm here to answer all your questions about probability and statistics. So if you have any questions about in that realm, for anywhere, high school statistics, probability, all the way up to college, whatever you want, any question that you want answered, go ahead and put them in the chat wherever you are. And remember to follow and subscribe to Chegg on TikTok, Instagram, YouTube, and Twitch. So yeah, I would love to hear from all of you. I thought to get us started, we would start with a statistics problem. So here is a statistics problem. I'm gonna read it out. You all can follow along at home. So the problem is, let's say I randomly um, get 400 people to run a mile, and I record their times. I get a sample mean of 9 minutes and a sample standard deviation of 2 minutes. What's a 95% confidence interval for the population average mile time? So this is a classic statistics question. You do some research, you collect some data. We want to extrapolate this the mile time that we saw from our data to the entire population. We want to say what's a reasonable upper and lower bounds for the mile time of the entire population. So yeah, you can go ahead and drop if you have a mile time. Go ahead and drop that in the chat, and let's see if it's how significant your mile time is. So yeah, let's see. So I'm just going to write down some notation first. That's pretty common in statistics. So the sample mean, often we're going to write that as x bar, and that's 9 minutes. What this is, you know, we don't need to use this for this problem, but the way that we calculate this, if you actually have the data, is you take the sum of all of the data points from I equals 1 to 100 to, let's see, 400, and then we sum them and divide by 400. So this is the average mile time of all of the data. Nice. So we're also given that the sample standard deviation, let's call that S, is 2 minutes. That, if you're curious, the way that you calculate that is you take the average squared deviation from the expectation, from the average. So you take xi, these are the mile times for each person, subtract that from your mean, square that, sum all of those across your entire data set, and take the average. For often you might see divided by just n, 400, but the sample standard deviation, technically we're supposed to divide by n minus 1. So we divide by 399. But that's not so important for this problem. That's just if you're curious about what the formula is. So let's construct a 95% confidence interval. The idea for this is there's basically a formula that we use. And what we do is we want to find a interval. The confidence interval is an interval in which the population average is likely to be in. So we imagine, in terms of, like, if we sample everybody in the entire world, we're going to get some average mile time. What is a likely interval that population average will fall into? That's the confidence interval. And specifically, a 95% confidence interval is the interval where we can under some assumptions, be about 95% certain that the population mean will fall into this interval. So yeah, so let's compute that. So the formula for this is what we do is we take our sample mean, and the upper and lower bounds. One way to write this often is we say the confidence interval is x bar plus or minus the what's called a z value, alpha over 2, times standard deviation, sigma, and divided by square root n. So if you like interval notation instead, this interval is going to be x bar minus z alpha over 2 sigma divided by square root n, comma, x bar plus z alpha over 2 sigma over square root n. So pretty simple. With these, actually, I'm going to, instead of this sigma here, I'm going to write an S, because that's the notation I used earlier. Yeah, so what these terms mean, I'm gonna go over what each of these terms mean. We know already what this sample mean is. That's what's pictured here. The sample standard deviation is given to us. That's something we compute from data. This square root n is the size of our data set. And this z, so this is size of data. Yeah, I'm seeing okay, from Potato on TikTok is going ahead and finishing up this problem. So yeah, that's definitely where we're headed to for part A. Yeah, we're definitely gonna get to that. So thank you. You guys have any questions about anything that I'm doing, or want to respond to anything that I'm doing, feel free to go ahead and discuss that in the chat. Yeah, so and this z value is called a critical z value. So this comes from a normal distribution. So, and this is something that we get from a table. This we read off a table. And some of you might be wondering, shouldn't we be using a t-test instead of a t value, instead of a z value, instead of a normal here? So often when we have a sample standard deviation, instead of using a z value, we actually use a t value, because that fits the distribution a little bit better. But because we have a lot of samples, we have 400 samples, it's safe to use a z value here as opposed to a t value. So typically, we're going to use a z value here because we have a lot of samples, even though we are using the empirical standard deviation. So let me just shut off a call in the back. I'll be right back. Okay, so yeah, so this is how we're going to get our confidence interval. So let's just plug in these numbers here. So we already know x bar, we already know s. Let's plug in, so n is going to be 400. That's given to us. And the z alpha over 2, what is alpha here? Alpha is the confidence level. So here, alpha will be 0.05, which it often is. This is what's called the confidence level. This is the probability that we're going to be incorrect, that the population mean will be outside of our interval. And we use alpha over 2 because it's if you're curious why we're doing this, this is because it's a two-tailed confidence interval. And so there's alpha over 2 chance that will be greater than the right-hand side, and alpha over 2 chance will be less than the left-hand side. So alpha chance total of being outside of the population mean being outside of this interval. And so this is z of 0.025, which we can read off from a table, and it turns out it's 1.96. It's a once you do enough of these problems, this is a one of those numbers that you just sort of know, but you can read it off from a table or look it up online if you want to. Yeah, I'm seeing Isaiah Pig Checo from TikTok saying 95% confidence. Yes, that's yes. It confuses some people sometimes because what does it mean to be? What does 95% confidence mean? This is one of the because statistics is very confusing. So this is one of those confusing things. But what it means is pretty simple. It means given certain assumptions about how we're sampling the data, specifically that we're sampling them independently, and they're identically distributed, there's about a 95% chance that this interval that we construct will contain the true population average. The population average is not random. It's just a deterministic number. So what's random is the interval. This interval is a random interval, and what we're asserting is that there's 95% chance that it contains the deterministic population mean. So that's what that means. I think it's sometimes a misconstrued notion, but it's not too. If you know exactly what it means, it's not too bad. So yeah, so we just go ahead and plug these numbers in. So here, this is the shorthand that often people use: x bar plus or minus z alpha over 2 s over square root n. Let's just plug these numbers in. So we get 9 plus or minus 1.96 times our sample standard deviation of 2 divided by square root n, square root 400. 9 plus or minus, so this is 2.92 over 20. So let me just go and plug that into my calculator real fast. We're going to get 2.92 divided by 20 is about, sorry, this is 3.92, not 2.92. There we go. That's what you get for trying to do math in your head. So 3.92 divided by 20 is going to be 9 plus or minus 0.196. So what this corresponds to in an interval, the confidence interval is 8.804 to 9.196. So that's the answer. This is we're about 95% sure that the true population average will lie in this. Let me know, does anybody have a mile time that's either greater than or less than this? Anybody have any cool mile times that they want to share in chat? We can go ahead and evaluate the significance of those mile times. Here I have one example. Let's say someone tells you they have a 5-minute mile time. That's pretty quick. It's a pretty quick mile time. What's the z-score of that result? And what's the chance that given this data, how many people in the population would have a mile time either equal to that or quicker? So as a disclaimer, this data I've totally I've totally made this up. This isn't based on real life. I think there's some truth to it, but don't go home and telling people that this is you know, a real study that's been done. We're just doing this for practice. Um, so uh, yeah, so let's see. So what is a z-score? So I think we had someone in TikTok chat post this earlier. I think Potato in the TikTok chat was posting about this earlier. Um, so a z-score is a pretty important concept um, in statistics, and it basically takes a sample and it normalizes that sample and puts it in a more contextual. It allows you to understand how much of an outlier a data point is, and all that you do with a z-score is you take your data, let's say xi, you subtract the mean x bar, and you divide uh, by the standard deviation, right? Um, this is also technically this is the z-score. You can technically a z-score is where you subtract the true, uh, the population average, but often what we're going to do is we're going to use the sample average and the sample standard deviation instead. And this is okay if n is large, right? If n is large, the sample average is going to be about the population average, and the sample standard deviation is going to be about the actual population standard deviation. So this is what a z-score is. So let's go ahead and compute it for this example. So now that we know, the formula, it's not so bad. We take 5 minus 9 and divide by the sample standard deviation. So that's 2. So we're going to get a z-score of, that's -4 up top divided by 2. That's -2, right? So can anyone tell me if this is this uh, significant or not significant? And how many individuals approximately would you think would have, given this data, would have equal to or quicker mile times? Does anybody want to hazard a guess or use some statistic knowledge to guess the how unlikely this is? I'll give a little moment to think. Go ahead and post it in chat or or discuss it in chat if you want to. Give you just a few more seconds to think about it. Okay, so yeah, so as some of you might have guessed, this is pretty, this is pretty fast. And uh specifically, it's faster than 9 minus 9 minus um uh so 2. So it's faster than 9 minus sample standard deviation times z 0.025. So this is the mean. 9 is the mean. The sample standard deviation is 2, and this z 0.025 is 1.96, right? So this is right. This is going to be like, me just plug that into my calculator real fast. So that's going to be 4.08, or sorry, 5.08. And the significance of this is this is the approximation for, so this is the about 0.025 probability of someone in the population should have a mile time faster than 0.008. So approximately probability that a random person has a mile time less than 9 minus 2 times z 0.025 is about 0.025. We're going to use about here. So we know that it's, and 5 is less than 0.025. And so probability that you have quicker than 5 is less than 0.025. And it's approximately. It turns out if you plug it in, probability that xi is less than or equal to 5, given these normality assumptions, is about 0.028. Looks like. Sorry, so 0.0228. Sorry. So that is 2.28%. Right. And the way that we get that is what we do is we take this probability that we want to estimate, and we turn everything into z-scores. So we take xi minus 9 divided by 2, less than or equal to 5 minus 9 divided by 2. So we're just doing the same thing to both sides inside of this probability. And we use the fact that this guy is approximately normal, standard normal. So this, is approximately the probability that a standard normal 0, 1, is less than or equal to -2. So this is, all approximate. Of course, this is assuming that mile times follow a normal distribution, which maybe they don't. It's not, not necessarily true, but it's an approximation. Okay, cool. Any questions about this problem that we did, or any follow-up questions? Let me zoom out a little bit so that we can see everything that we did here. Just drop any questions or any follow-up questions you have in the chat, if you want to go into this a little bit further. This is being able to construct confidence intervals and evaluate z-scores is a pretty fundamental topic in statistics. So it's nice to get a good understanding of this. Yeah. Back in high school, I ran a 4:32 miles, so I was pretty happy about that. I thought I was pretty quick back then, but not anymore. Not anymore. All right, cool. So just if you're just joining us, I am Doug Dow, and I am a probability PhD student, and I love thinking about probability. My research is in probability and statistics, and I would love to answer your questions about these topics and try to help you in your classes. And this is Chegg Office Hours, and we're here every week, and we have lots of different really cool topics pretty much every day. So make sure to follow all the channels on TikTok, YouTube, Instagram, Twitch, to stay up to date with all these cool office hours. So yeah, and ask away any questions that you have in chat, or any topics that you want to go over. So yeah, I thought that we could do another statistics one. Let me just write here, chig prob plus stats office hours. Yeah, awesome. So I thought we could do another statistics question. Last week we did a few probability ones, so I thought this week we could do a couple of statistics, give that field its due. Okay, so let's do the following one. One thing you'll notice about these statistics questions is that they're really, when you get down to it, the math is not that hard. It's more knowing what formulas to apply and when to apply them. So statistics is not a really hard math subject. It's more of a understanding subject, and it's harder to understand it. But once you know the formulas and understand when to apply them, you're gonna crush all the problems. So let's do this question. So it's this question that I came up with. Again, this data is totally artificial. I didn't actually go out and measure pigeons in New York, but I want to know. Let's say I want to know if New York City pigeons are on average larger than typical. Let's say the average weight of a pigeon is about 4 pounds. I did look that up. That's about right, apparently. It depends on the pigeon type, but I just took a nice round number, a nice whole number. So let's say I promise I didn't do this. I capture and weigh 5 pigeons in New York City and record their weights: 3, 4.2, 4.7, 5, 5.5, all in pounds, imperial units. Can I conclude using hypothesis testing methods that New York City pigeons are larger than typical with 95% confidence? So this is again a situation where we're going to take this data and we're going to construct and we're going to use statistics to try to test a hypothesis. So what is the hypothesis here? Whenever we do hypothesis testing, we want to declare what the hypothesis, the null hypothesis, that's this H naught, null hypothesis. This is the prior, the thing that we start with. It's not necessarily the thing that we think is true, but it's the thing that we're trying to disprove typically. So here, the prior, this sort of null case, is that the pigeons in New York are the same on average weight of the pigeons in general. NYC average weight, average pigeon weight, is same as population. So this, again, this is usually it's something that we're trying to disprove, actually, which is a little bit counterintuitive, because why would that be where we start? But the way statistics works is we try to make it hard to establish truth. We want to have a high bar for truth. And so we start off assuming that we know nothing, that we have no biases. That's the idea. And then we try to find data, or we find data and we see if it disproves our null hypothesis. We don't. It's bad to go and search for data that will disprove. That's called data mining. That's not good. But you want to go out into nature and just observe the world and see if it disproves your null hypothesis. And usually we'll have an alternative hypothesis. You don't have to have an alternative hypothesis, but it's typical that you do. This just narrows the scope of what we're trying to establish. If you've ever seen court rulings, often they'll limit the scope of their ruling because they don't want to mess with the entire judicial system. So they'll often try to do a very narrow ruling. This is what we're trying to do. We're not trying to just solve all the problems in the world. We're just trying to disprove the null hypothesis, and this is our alternative. And in this case, the alternative, we can interpret this as the alternative is NYC pigeon weight is greater than average. Right? That's given to us in the problem. Again, this is sometimes it's not the alternative hypothesis is just the NYC pigeon weight is just different than the average. But in this case, we specifically want to know if the pigeons are larger. And so here we say the alternative hypothesis is the pigeons are larger than average. And this will become important when we do the hypothesis testing. Okay, so yeah, so I have from Potato on TikTok is saying sample mean is 4.48 standard deviation, around, sample mean 4.4, standard deviation around 0.952. Yes, I think this data is correct if it going off my my personal, except I think the t-test is, my t-value is slightly different. So we'll talk about why that might be. But it could just be I wrote down the wrong t-value also. But let's work through it. So yeah, so let's work through that. Yeah, so here as Potato on TikTok is suggesting, we're going to do a t-test rather than like z-test, meaning we're not in the previous question we used z-scores, but here we're going to use t-scores. And the reason is because our sample size is very small. And so we're going to use t-test rather than z-test. So let's talk about that. So first, so the t statistic that we're going to use is the following. It's going to be the sample mean minus the population mean, so minus 4, and then divide by the sample standard deviation and yeah, so and then we multiply by square root of 5. So yeah, right. So so we need the sample mean and the sample standard deviation. So let's go and find those values. So the sample mean, we're gonna just plug this into our calculators. 1/5 times the sum of the data. So 3 plus 4.2 plus 4.7 plus 5 plus 5.5, right? So let's go ahead and plug that into our calculators. I think someone in chat already said it. If you have it also, go ahead and plug that in. I got 4.48. So that's the sample mean. And yeah, so and the sample standard deviation, this is the formula that we used earlier. We're gonna take the average squared deviation from the sample mean. And this caveat here is we're gonna divide by 4 instead of 5. Divide by n minus 1 here. That's just the small difference to what you might expect. Usually you would divide by 5 there intuitively, but because we're taking some average, but for some subtle reasons, we divide by 4 there instead. 4.48 squared plus 5 minus 4.48 squared plus 5.5 minus 4.48 squared. Okay. And okay, I believe I have the value for this, which I think, yeah, someone posted in chat also. So it's let's see, 9.0.952 is what I got. So yeah. So that's what Potato from TikTok got on in chat also. So yeah, so that's the sample standard deviation, and then yeah, so then we're going to evaluate our t statistic. So see, we're gonna plug these numbers in to here. So 4.48 minus 4 divided by point. Sorry, this is the sample variance, and so we need to take the square root of this for the sample standard deviation. That's a subtle point here. So we take the square root of this, so S is square root of 0.952. It'll be pretty close to it because it's close to 1 anyway, so taking the square root doesn't change much, but yeah, so that's that. And then I get a value of, just going to plug this in. If you have it before me, just let me know. And let's see. Okay, so let me just okay, yeah. So I get a 1.10 for this, right? And the critical t-value, what we're going to do, so this is something that is easy to get confused on. So we're going to use, we can look at these tables for critical t-values, and we need to know the degrees of freedom when we look at this up in the table. And the degrees of freedom here is n minus 1, which is 4. And so maybe I can share this. Just share this t-value table. So here we go. So this is, so we just look this up, right? Or it's in a textbook, or use your calculator. So here on the left, this is the degrees of freedom. So here we're going to go to this 4, because we have n minus 1 is 4. And then we're going to go across. And what these values mean, it says right here, this is this value, the probability that the t distribution with degrees of freedom 4 is less than, this value is equal to 0.95. And so if you think about that, the probability that's greater than that value is 0.05, very small. And so what we're going to do is we're going to find a value that such that the probability that our t statistic is less than or equal to that value is 0.95. And if it's greater than that value, we say that that's unusual, because under the null hypothesis, there's only a 5% chance of that happening. And so we would reject the null hypothesis at the 95% threshold. And the reason here that we're using 0.95, which is instead of 0.975, is that we're doing a one-tailed test, because we only care, our alternative hypothesis is only is that the pigeons are heavier than average, and so we're doing a one-tailed test. So so this is 2.132. So let me go and go back to the whiteboard here. So t of 0.05 of 4 this is just my notation for the critical value of the t-distribution with degrees of freedom 4 at the 0.05 level. This is 2 point, I already forgot what the what the value was. This is, I think it was 2.132. Okay. Okay, so that means that because our t-statistic is less than this value, we're not going to reject the null hypothesis. Because let's say an absolute value. We do not reject null. Okay, so and the reason is like because there's a pretty decent chance that under the null hypothesis we observe this data. It's not that crazy, right? It could be that pigeons in New York are the same size as same weight as pigeons around the world, and we observed this data of pound, 3 pounds, 4.2 pounds, 4.7, right? We can't rule it out at least at this level, at this 95% confidence level. Okay. So, and that's the subtle thing that I want to communicate about statistics is that it's not that we believe that the null hypothesis is true. I've seen pigeons in New York that are larger than my head. And I don't think that the null hypothesis is true just in my gut, but I cannot, using this data, I cannot reject the null hypothesis, right? So if I'm being a good statistician, I'm going to remain neutral. I don't know either way, basically. So I haven't proven it. I haven't disproven the null hypothesis. We don't have enough data. We haven't rejected it yet. Okay, does that make sense to everyone? Let me know if you have any questions about that, or want to clarify anything that we did there. And go ahead and tell me, which city do you think has the largest pigeon population? Or have you seen any crazy pigeons in your life? That's what I want to know. But yeah, anyway, so yeah, and feel free. So if you're just joining us, this is Chegg Probability and Statistics Office Hours. We're having a fun time talking about some statistics, testing null hypotheses. I'm here to answer all your questions. I'm a PhD candidate from NYU, and I love talking about statistics and probability. And I think it's super practical in all aspects of life. And so I want to answer all of your questions and talk about all the problems that you have in either your classes, your homework, your exams, or just applications in whatever field you're studying. So feel free to post those in the chat. And also, we have a lot of these live streams going on at Chegg. So go ahead and follow Chegg on YouTube, Twitch, Twitter, or not Twitter, maybe YouTube, and Instagram, TikTok, and to stay up to date. So let's go ahead to another question if there's no suggestions. Prob stats, OH. So I thought we've done a couple. So I have one more statistics problem for us all today. So let me go ahead and upload that. Okay. Here we're going to talk about chi-square tests, which is a little bit less known, I think, than t-tests or z-tests, but it's important and it's useful to know. So the chi-square test, there's a lot of different chi-square tests. We're going to talk about today the chi-square goodness of fit test. So this might be a problem that you see in homework or on a test. This is a common type of problem in statistics. Um, so what we're going to imagine is I'm going to go out and ask 100 people to give me a uniform random number between 1 and 5. And I get the following counts. So these counts, hopefully they add up to 100. And so for instance, what this means is 27 people answered 1, 19 people answered 2, and so on. Can we reject the null hypothesis that the sampled individuals chose integers uniformly at random? So there's some discrepancies here. We would expect just 20, but it's not 20, counts. So is this truly random or not? So just as an experiment, what everyone in chat, do you want to post a random number? Try to come up with a totally random number and post it in chat, and let's see. You can see if the numbers are truly random. If we get enough, we could do a chi-squared goodness of fit test on the Chegg office hours watchers. See if you guys are actually random. But the point is, so what are we going to do here? So we're going to do a chi-squared we're going to use a chi-squared statistic. So it's this thing called chi-squared goodness of fit test. And what this test is, it relies on the following statistic. So chi-squared is, this statistic is defined in the following way. It's the sum over all the possibilities, so that's I equals 1 to 5 of the observed, so it has the following formula: the observed value, that's O, minus the expected value, E, squared, divided by the expected value. So OI is observed value. EI is expected value. So this is the statistic, and yeah, I'm seeing from TikTok, Potatoes saying 3 for the random number. I think that's pretty random. Let's try to get a few more in. I think 3's, it's a decently random number. I would say it's one of the more random numbers out of the 5. So yeah, that's a good effort. So yeah, try to just be random. It's actually pretty hard to be completely random. But yeah, that's a good start. 3 is very random. Yeah, so here, this is the statistic, and the idea is the expected value here is what we would get if the null hypothesis is true. The observed value is what we actually see. So speaking of the null hypothesis, let me go ahead and just write those down, because that's always what we should do to start. And I kind of missed that. So the null hypothesis here is counts or numbers are chosen uniformly from the set 1, 2, 3, 4, 5. That's our null hypothesis. And in here, our alternative hypothesis is not quite as precise as the previous question. Our alternative hypothesis is not H naught. We don't really have a clear alternative, right? We could if we wanted to, right? We could say, I think people choose 1 more often than average. So we could do that, but in the way the problem is phrased, it isn't very clear that there's an alternative. So we're not really going to specify that here. Okay, calculate this statistic. So chi-squared. So we just plug this into a calculator. We write down the first few terms. So we get 27. So, okay, what's the expected value? In this case, it's going to be 20 because if people chose numbers 1 through 5, just completely uniformly random, there'd be about a 1/5 chance of it being any particular number. And so the expected number of count of any of them would be about 20. So that's going to be the same for all of them. So we follow this formula. So 27 minus 20 squared divided by 20 plus 19 minus 20 squared divided by 20 plus ... We do all these. Maybe I won't write them down all. I hope you get what I mean here, where we just calculate this. And what I got is 12.2 when I did this. Feel free to do this at home too to make sure you get the same number. So what does this mean, right? Like 12.2, what does that mean? It's hard to tell you what, is that a lot? Is that a little? That's the point of statistics, is to try to tell you, is this unusual or not? Can we reject the null hypothesis or not? In a rigorous way, in a mathematical way. So okay, so we're going to use this chi-squared statistic, and so we got this. The statistics theory tells us that this random variable is distributed, at least approximately, equal to a chi-squared random variable with degrees of freedom n minus 1. And here the n, I guess it's a little bit confusing, but here the n, it does not refer to the number of participants. It refers to the number of baskets. So here the degrees of freedom is actually 4. It's the number of baskets that we can put the counts in. So that's just a small point here. So yeah, and this is under null hypothesis. Under the null hypothesis, this statistic is a random variable that follows this distribution. So then we go and we measure it. So we see 12.2, and we ask, is this unusual? Is this random variable under the null hypothesis, is this unusual or not? And we do that by, one way to do that is to record the p-value. So what the p-value says is, in this case, it's literally the probability that under the null hypothesis that the statistic is greater than or equal to the observed value. So what's the probability that under the null hypothesis that we get something more dramatic than what we saw, right? You just check the chat. Yeah, okay, so yeah, for those just joining, we're coming to the end of the Chegg probability and statistics office hours. I'm here to answer all your questions about probability and statistics. We have a few more minutes left, so make sure to get those questions in and ask me. I love talking about probability and statistics. I think it's super awesome and very useful. And so go ahead and get those questions in. And also make sure to come to all the other Chegg office hours also, and follow Chegg on Twitch, TikTok, Instagram, wherever you get your Chegg content. So this is what the p-value is. And in this case, so again, we either look this up from a table, or we there's CDF calculators of chi-squared, wherever you get your chi-squared content. You get your Chegg content, you got to get your chi-squared content somewhere, Wolfram Alpha, wherever you get your chi-squared content. And the one that I wrote this down earlier. I got 0.015 0.0159 is what I got. So let's see. So here, does anybody want to say whether or not we should reject the null hypothesis given this p-value in chat? Why don't you debate over whether should we reject the null hypothesis that these numbers were chosen uniformly at random if we have this p-value of 0.0159? Is that sufficient to reject typically? Go ahead and answer in chat if you have an idea. I'll give a few more seconds for people to get stuff in. Okay, 5, 4, 3, 2, 1. Okay, so yeah, so it turns out that we should reject the null hypothesis at the 95% confidence say, because I need to go to English class, because p is less than 0.05, we reject h naught at the 0.05 level, which is a typical level. And note that we actually wouldn't reject this not at 0.01 level. So that's a stricter, that would be if the p-value is less than 0.01. So we don't reject that level, but 0.05 is typically enough for most people. So we are going to reject the null hypothesis. And this rigorously tells us that this data set is abnormal under the null hypothesis. This is unlikely to occur. And so we say probably like the null hypothesis isn't true. Now, sometimes even if the null hypothesis is true, you'll get data that is this weird, but it's unlikely, right? And exactly how unlikely? Well, it's about 1.59% chance under the null hypothesis that we would see data this weird. So that's what the p-value tells us. It's how weird is the data. Can you help with combinatorics? I'm seeing from Pickles from TikTok. Can you help with combinatorics and probability? Yeah, sure. So looks like we have a couple minutes left. So I'm not sure how much we can go into this, but yeah. Actually, last week I did a few combinatorics questions. Let me so I can briefly, because I got a chat about that, briefly talk about some combinatorics ideas. Actually, this is a little bit complicated, so maybe I won't do that one. But yeah, let me just talk about some class. So let me try to find a good question there. Okay, so let's do. This is a question that I had last week, but we can change it up a little bit or talk about how you might approach questions like this. So combinatorics is the field of probability about counting things, and often, for when we count things, let's just talk about the most basic. How many 5-card hands are there in a 52-card deck? Let's just do that before we end. So 2-card deck. How many 5-card hands are there? Not caring about order. Well, in that case, it's 52. Choose 5, and this is number 5-card hands without order. So this 52 choose 5 is a very common thing. Like this n choose k is the number of elements from a set of size n of size k without ordering. So that's a very, very common combinatorics concept. So yeah, I would love to help with more combinatorics. I love combinatorics and probability. come back next week, and we'll do a bunch more of that. I have lots of fun questions, and also you can go to Chegg. I'm sure they have lots of resources. But yeah, I would love to help you out with that next week. And yeah, so thanks for coming to the Chegg probability and statistics office hours. It's been great chatting with you all, and going through some questions. And I hope you all learned a lot. Remember to follow Chegg on TikTok, YouTube, Instagram, Twitch to get updates on the next live streams, and to go to the other live streams and see see what you can learn. So yeah, thanks so much.